All right, now in this video, I'm going to be talking about functions of several variables. And for the most part, especially at the beginning in this class, we're going to be investigating functions that take in two real numbers and give you back one real number. That's z equals a function of x and y. Okay, but first I want to just, kind of write down a few examples of functions of several variables that you may already be familiar with. First, and one of my favorites, because you've been knowing about this for a very long time, right? This is a rectangle. And I guess that would also need to be right to imply that was a rectangle. And that the top and bottom are parallel. But yeah, you got a rectangle, this is x, that's y. The area of this rectangle depends on both x and y, right? I could pull this way and I could increase x and that would increase the area. I could also decrease y and that would decrease the area while holding x the same. So I can say that this area function, area which depends on both x and y, is equal to x times y. Okay? Don't really know how to draw such a, I don't know, maybe I'll give you just like a cloud. One of the few things that I feel like I really took away from the only chemistry class I ever took, which was in the 12th grade, and it was a good chemistry class. But one of the things I really took away from it was the ideal gas law, because it made a lot of sense to me. Yeah, exactly. And it was one of the few things that I felt like made a whole lot of sense to me in that class. So we know that PV equals nRT for an ideal gas. I had to look it up. The R is evidently capitalized. Yeah, according to chemists. Small r must have some different meaning. Yeah, I get it.
R is
a constant.
So if you want, yeah, I knew that, but I knew what they all meant, but I didn't know if it was stylized with a capital or lowercase. But the temperature of a gas, we could express in terms of its pressure, volume, and the amount of gas, number of moles, yeah. I always felt like the arbitrary amount to choose for, like the standard amount of a chemical. But I think it was I just didn't go far enough in the subject to figure it out. Oh, I'm saying that temperature depends on pressure, volume, and number of moles, where R is just some kind of constant. And T, using some old-fashioned Algebra 1, I'm going to say T is PV over NR. Probably, I don't know, since R is a constant, we might put that in the front, but who knows, That's an example of a function of several variables, a function of three variables that you're already familiar with, because most of y'all have taken quite a bit of chemistry in this class. I also would say, speaking of temperature, I could talk about the temperature at a point in space. You can visualize that. You can visualize space, and you can know that temperature is kind of variable. It might be significantly colder in Canada than it is outside right now. But I don't know, you may have also seen on the Unit 1 test how there was this question, I had a space curve. I don't know what I was thinking when I asked this question 2 years ago or whenever, but it was like based on the velocity vector, what direction is the object headed? And what I needed to say was we need to assume a flat world where the z-axis is the altitude, because northeast, as far as some sort of like absolute x increasing, y also increasing, doesn't necessarily mean the same thing if you're looking at something across the back of the globe. And so what I'm going to point out is that, temperature in space we could maybe get a better coordinate system. And that's just something I want to mention, is that we will eventually replace this with spherical coordinates, and it will make things like
Longitude, latitude.
yeah, well, true. Yeah, you're going to need two coordinates for the surface of a sphere, but it will make some things like, direction on Earth make a little more sense if we have, some sort of better coordinate system. That was something I just, put on the side of my lecture notes and make sure to point that out. Another thing that y'all are familiar with, or you could imagine, is the wind at some point in space, right? Or the gravity in some point in space. But I'm going to tell you that this is not something that we're going to be studying at this point, right? Because the wind would be a vector. It's going to be, have a strength and it's going to head in a direction. So I could say the wind at point X, Y, and Z, this is a vector field, right? Because it's going to take in a vector and it's going to give us back a vector. And we will study that in this course, just not yet. Okay. So, and then another thing that I want to be, real specific about kind of at the outset. And I talked about this a lot in the linear algebra class, but again, I have some new joiners. So when we talk about a function like this area function, I'm going to take out this x and put it up here. This area function takes in two numbers and gives you back one. So it takes a two-dimensional vector and gives you back a real number. Okay, and we are going to ideally be stylizing our functions, talking about their domain and codomain. The domain is, what types of things does this take in, and the codomain is what does it give back. Okay, and I'm going to hopefully go in on the green one. This is going to take a three-dimensional vector and give you back a real number. So this t function is going to take R3 and go back into R. Okay, this would maybe go R3 to R3. Okay, this w function. Okay, but I just want to talk about, clearly labeling our domain and codomain when we go to name a function in this class. Because will come a point where that distinction is important. Maybe not as important as it was in linear algebra, though, I will say. All right, so I'm going to talk to you about graphing functions of several variables. I'm going to start with a couple that I can draw by hand. For the most part, we cannot, and so we're going to have to, include some sort of technology tool. Me personally, especially this year, since we got a lot of computer stuff going on, I'm going to be using the GeoGebra 3D calculator for, and I remember that was maybe like a bad word or something in here, but it's all you do is, really what I did was I went to Google and I put in 3D Grapher and it was the first link and I liked what it gave me, so that's what I'm going to stick with, And so, but I'm going to start off with, graphing a couple of them, like f of x and y is equal to 5. We can graph this thing, all right? Just envision, remember z is oftentimes what we would consider to be, the output variable, much like y was in the past. So z is always 5. We'll just think that's just like, everything's 5 above the ground. So it's going to be a flat plane. And I can draw this, or at least attempt. And then I'm going to mark clearly this 5 right there. And then I'm going to put a parallelogram around it, I hope, that looks right. It's got to be parallel to this thing. Okay, I need to erase that, right? For the perspective, that's pretty decent. And I think it looks really good on screen. So, okay. That's one successful graph drawn in this class. Yeah, I'm going to hold on to that. And then another function I might be interested in talking about, g of x and y, is like 5 plus x squared. Okay? This one I'm not going to draw you a picture of, right? Because then think about this one doesn't really care about what y is doing. So if I have x and y, what this is going to look like is, well, it's going to kind of look, I'm going to take out y. Take y out of the situation, not out of the equation. And I'm going to graph z versus x. Okay? Now this is one technique that we can employ sometimes to get a picture of a function, is just kind of draw a trace in one plane. But we know what 5 plus x squared looks like, right? It looks like that. And so what I'm saying is that we're looking at it from the front, right here, 5 plus x squared, and it's going to not care about what y is, so it's going to kind of be a sheet in y. It's going to be a parabola, except that we've extended it forwards and backwards. And I don't trust myself to draw that very well, but I think that y'all can envision it yourselves. But what g of x actually wants to be, as far as like my example and where I'm going with this video, is I want 5 plus x squared plus y squared. Now I've got a question coming from the crowd. Yeah. Thank you. It was more of a comment from the crowd, and it is a taco and y, and I cannot express a better, it's an infinitely long taco, but it is going to have a very taco-like shape. So thank you for that. Yeah, I really do appreciate that. And I'm going to say this is 5 plus x squared plus y squared. This is going to be more interesting for me, and this is something that I could draw. Or I'm going to try. This is x. y, and here it is z. It's not very straight z-axis, but all right. So it's going to start at 5, and as x and y get bigger, we know that z has to get bigger because x and y are both squared, so it's just going to like, z is getting bigger. And what I'm going to tell you, it's a paraboloid. And because it looks like a parabola, but it's a solid.
That's a fun word.
Okay, I'll keep that in mind.
Was that taco parabola?
It was a parabolic sheet, I believe is what you would call that. All of these figures have names, and none of the names are very important, in my opinion. Okay, but I'm not some sort of like analytic geometer or anything. So it kind of looks like this, and it's solid. Okay? And so what I'm gonna honestly,
You take a parabola
I'm liking this.
and then you just rotate it around the z-axis.
Ooh, that's a thought. That sounds reasonable. Comment was take the parabola and rotate it around the z-axis. I mean, it's very circular. And you can see it's got circular aspects because the x squared plus y squared, and I do have more to say about that. So I'm going to, okay, here we've drawn a graph. I'm going to take away f of x and y equals 5 and all of these examples over here, but I am going to leave g and its picture because I'm going to be talking about this function quite a bit more. This eraser got some of that magic whiteboard solution on it. It's a little crusty. No, I mean it's like sounds kind of dry when I'm erasing, but who knows? Maybe it's just seasoning the whiteboard as I erase. All right. So I'm going to define a level set. Okay. So one thing and this is going to be useful to us at various points in this course.
Mr. Rutherford, can you not use green?
Yes, I forgot. Okay, yes. Please don't use green. I need to go back to the chalkboard. That's where I get the best contrast, it looks like, having recorded a couple of videos at each of the different stations. I think that the chalkboard is best, just for a contrast. Everyone's seeing things. Okay, so I'm going to define. I'm used to defining in green for a few years now, so I need to get a different color. I'm going to define a level curve. So how did I say? Okay, so f is going to take a set x to a set y. You know, it could be a space. It could be, all sorts of things. The level set f equals c, where c is some element of y. It could be a vector, it could be a number. For this point in the class, we're seeing, obviously, it's going to be a number, right? But the level set f equals c is the set is going to be the set of all x's in the domain. Maybe vector, maybe not, for which f of x equals c. Okay, so let's take it back to algebra 1, right? I'd like to do that. For example, let f be a function that takes in real numbers and gives you back real numbers. You know, it's one we like to talk about a lot. F of x equals x squared. Okay, the level set corresponding to f equals 10 is the set of, well, basically negative square root of 10 and positive square root of 10. For f of x equals sine of x and f equals 0, it's going to be like, I don't know, multiples of pi or something. Okay. But I'm also interested in talking about the level curves, or excuse me, the level set over here. Okay, so the level set g equals 10 I get by setting 5 plus x squared plus y squared equals 10. Okay, so 5 plus x squared plus y squared equals 10, which is where x squared plus y squared was equal to 5. Now, I could kind of envision if, say this was 10 right here, just for convenience, this like kind of arc here. This was the flat level z equals 10. If we took that and kind of projected down onto the xy plane, where are we getting there? We're going to get a circle. If you think about this nicely rotated parabola, like you said, makes sense. Okay, and these level sets, especially when we're taking in two variables and mapping them to a real number, the level curve, they're going to be level curves, okay, in the plane. Okay, and what else did I have to say about that? And then this level set, when we're taking z equals f of x and y, you might also call this a contour curve, okay, or just a contour in other contexts. Because a function of 3 variables will have level surfaces. And I think I'm also going to say that a contour map depicts the level curves of f on its domain. So I'm going to go and I'm going to make a contour map for G. And it's not going to be that hard. I promise you that I can make a good drawing of this one. Okay, so what we do is we're going to draw the contour map on the domain. And G is a function that takes in 2 real numbers and gives you back 1 real number. So our contour map will live on R2. And we're very good at drawing on R2. We have so much practice. That's x, this is y. And we saw that the level set G equals 10 was x squared plus y squared equals 5. It was the circle centered around the origin with radius square root of 5. So, okay, and this is C equals 10. Okay, for different values of C, we'll have different sizes of circle, but they will always be centered around the origin because this calculation is going to go the same way, right? Let's talk about C equals like 1 or C equals 0. It's going to be the level set for C equals 1. When can 5 plus x squared plus y squared equal 1? That would be never, yeah. So there won't be a curve for that.
Well, if you look at the graph, there's nothing at.
Yes,
equals
also.
1.
Yeah. So and that calls back to kind of how I think about it. If you've got, especially in the z equals f of x and y case, if you've got the picture of it and you're kind of just cutting across at a z level, if you don't hit it at all, well, you're going to have an empty set. It's also related. It's the pre-image, okay, which is something that I think we may have talked about a little bit in linear algebra. Or maybe I'm getting it confused with, some topology discussion in the fall. Okay, anyway, there will be other ones like, I don't know, C equals 9, I think will have a nice radius of 3. Which,
Really?
yeah. Sometimes you have to think about those things a little harder when you're standing up here with a marker. All right, so that's C equals 9. What about C equals 5?
Be a dot.
It's the dot at the origin. All right, I think that's all I have to say about this. You can draw in as many concentric circles as you want, but you're not going to get any additional information from them. Okay, what else did I want to say? Oh, I did the contour map for that, and I'm just going to cap off this video, and I have just the right amount of time, with a discussion of the Cobb-Douglas production function, which this class, I'll be honest, most of the applications are to physics. And, if you're a physicist, you'll, have all sorts of good use for this. And if you're not, who knows? But I did, at the tail end of my time at the UW, I took a microeconomics course that was like, I don't know, it had some math, and it was why I signed up. And I was just really looking for classes that would help me finish, right? Trying to get a degree. had a whole lot of this level of calculus on it, like partial derivatives, easy double integrals, and I thought it was pretty easy. And there were lots of really good Lagrange multiplier problems, which is something that we're going to do with partial derivatives. But one thing I want to tell you, because I'm not exactly sure how much economics y'all have had, and to what degree we go at this school. So I just want to talk about the Cobb-Douglas production function. Is like the level of production is going to take in two real numbers and give you back one real number, where its factors are labor and capital. So it's like the amount of money you spend on labor and the amount of money you spend on like machinery or rent. Or
Like this?
it's, I don't know. I think that you've seen at least this shape before. And it's, some constant times L to the N and K to the 1 minus. And basically these exponents have to add up to 1. They're like fractions or decimals or something that add up to 1. And this C, I remember it had some sort of a meaning economically, I think. But if you're interested in this, take a microeconomics course. I actually found it to be quite interesting, and I found the math to be very easy, okay, very friendly. Okay, what was I going to say about this? Oh, the level curves of this guy look like this, and I was just wondering if y'all have seen this shape before. Okay, so for a very small production, it's like this, and then it kind of. And I believe that these are these utility curves? But have you seen?
What does the X and Y axis mean?
I believe that that's going to be labor and capital.
Okay, so
I mean, it doesn't really matter because they have symmetry. At least up to this, it's pretty balanced.
We've seen it as like upside down parabola.
Oh,
Labor
interesting.
In production, it's the production possibilities curve.
Interesting.
Like
I believe
how
that
much
this
capital and consumer
is also related to the demand curves also, I think. But
Have you talked about it in micro?
okay, I don't want to go too far and say the wrong thing, but this is the type of thing that if you're an economist or interested in becoming an economist, this type of mathematics is actually useful. And that's all I got to say about functions of several variables for now.